So the stage is yours.
Thank you. I'm one of the deputy organizers. Daniel is the organizer. I come from the GMUM group of machine learning, and I'm happy to see today Tabor, who is the boss of our group, and he leads. He's the leader. He's a mathematician. I'll take you on a journey through deep learning and through the current research in it, and perhaps something about what we may do for you in machine neuroscience, or perhaps the other way. But I'd rather talk about deep learning because this is what I know something about, not the neuroscience. The first thing I wanted to say that there are two types of research. One is the hypothesis-driven, where you have some set of rules, and the set of rules you try to find the set of rules and build an algorithms for. I'm talking from the machine learning point of view, rather. Extract some rules. For example, we have such digits. This is called the MNIST data set. And we extract some features that the 6 is something around a circle and some something coming from that, and then we might need some algorithm which extracts the features, tests the features, and then says that it is a 6 or 9 or whatever. But then we might also have a data-driven approach when we simply take a number of examples and use some generic algorithm, a simple algorithm which will be repeatable, will be the same for different problems, and then find some model which will evaluate the numbers and find which number is which. So we shall build a model which will be usually a kind of a black box. It will just take the input and give an output without explaining it. Explanation in deep learning is something, a different topic, which is recently it has gained much attention. I will come to that later. So one thing is important: the model shall select its own features, the features which are really important for it to classify the numbers, for example, and then these might not be the features which we shall select in the hypothesis-driven. It might be something completely different, but it will depend on the data set, and this might be a problem. So, one thing I wanted to say that there are a number of tools actually which are which use machine learning, and there are tools which are used in neuroscience also. I took an example. This is the pose estimation. You know this better. You have a cage with some rodents, and you want to track how the rodents move. And for example, there is the Mattis and his group have developed a package. I hope there will be the name of the package. Because, yeah, that's right. I forgot it for a moment. And it is a fantastic package which is not based on the hypothesis. It doesn't use some predefined rules how the rodents move and whether the rodents shall move right, and predicting from these rules. It is rather observing the data And from the data, the rodents, as far as I remember, are marked in some ways. They have some points on the back, if we used some of these rules might happen not to be important. So it might be good to do it in the data-driven way. It also might be, well, it comes like that, that there are pictures, the movie with rodents. It is being implemented in a model which is called the encoder-decoder model, which is simply means that the picture, the image, is encoded into a latent space, so-called latent space. I'll give you some other examples of that, which is a representation of the image, and then it is decoded again, so that we can put some estimation on that. It is with some kind of experts, I mean, and then it understands how the mouse moves. And then it will be doing it for, are you nervous already?
No, I wanted to show you, you can press.
Yeah. The laser here. I forgot about that. Thank you. I thought it was already 10 minutes to the end. So it's just as I said, so it is the latent space which encodes the information which is important. It doesn't encode the information which is unimportant. For example, it doesn't encode the information on the, for example, of the floor, which is below the rodents, probably. I'm not really sure about that. The problem here is that the data sizes might be large. I mean that we might need a lots of data to really develop a fully working model. So this might be a problem. We shall come to that again. So let's come back to the machine learning and what really deep learning is, because everybody is using the term deep learning and nobody really understands what we talk about different things using the notion of deep learning. So first, I wanted to say that there are some different tasks which are solved with machine learning approaches. First, there is the clustering, that is the assigning some data into different groups, and this is usually unsupervised learning, we want to find some statistical rules which simply tell which of the examples are different from the other and which of the examples are very similar, which might be grouped. And then the expert afterwards, the clustering, an expert comes and labels each of the clusters, says these are mice and these are rats and these are whatever there is in the data. Then there is a classification that everybody understands. This is for example, the MNIST data set with the numbers classifying into regression, which is simply a function evaluation. Association rule is a problem where we have to associate some data with the rules which people do. The problem is which might be simple to understand is the basket analysis. The people are coming to a shop, buying several things, and then the people at the market need to know what to place, how to place things in the market. For example, there is people buy vodka, they buy caviar, and then we want to find a rule whether they'll be buying it at the same time or not. There's a causal inference whether they should buy a caviar if they buy vodka. If it is so, we can place the caviar nearby so that they will be buying it again. Or the other way around, so that if they buy caviar always when buying vodka, place it on the other end of the shop so that they would pass the shop and buy several other things on their way. Usual, that might be even more usable. Dimensionality reduction is something you do all the time. That is, for example, the PCA algorithms find some rules in the dimensions in the data set which are important, which might be important for the task that we are solving. And some problems, another models are the generative models, which try to find the distribution of the data and then even decide on what other objects from the same distribution might be generated. We shall come to that. I'll give you some examples because I think it is fun. And then these are the tasks, and these are now the usual approaches. One is the supervised learning, where when we have as data, we have some input objects and the labels which are associated with them, and then the model has to learn how to associate find a true label for a given example. And so there is this is not so we have an environment, then we get from the environment the data. This data comes to the learning system. The learning system gives some response. And at the same time, the teacher tells the true answer. So we have number 6. It is being classified by the system as a 3. The teacher tells it's a 6, so we have an error, which is calculated in whatever way. And then the learning system has to adapt the weights, the parameters.
Как ты можешь купальник надевать?
It's mine? Yeah. So the learning system moves somehow, adapts the parameters so that the next time the answer would be better. Then it is usually done with some gradient descent algorithms, which are actually the generic algorithms used in probably most of the, if not all, approaches to learning. We shall talk about that. But the gradient learning is efficient compared to other methods, but on the other hand, it is very slow. It is a kind of a system to. If you read the book of Daniel Kahneman, you know what the system 1 and system 2 is. System 2 is something which is, we shall come to that, but it is a slow type of learning. And then we have several algorithms which will, and gradient learning is not plausible biologically. This is another problem, perhaps a problem with neuroscience. Then we have the reinforcement learning. I will skip generally the reinforcement learning, all the slides that I have done, because Eleni will be talking on reinforcement learning shortly, but I will give some examples about that. But actually, the difference here is that the environment does react to what the agent, the learning system does, but it doesn't give a true answer. It only tells us about whether we are doing correctly or not correctly, and usually it tells us that it tells it at the end of a whole episode, the so-called episode. Well, we had a fantastic lecture the day before about reinforcement learning. And then in deep learning, there is lots of examples of using reinforcement learning paradigm with playing complex games. I will give you some examples of that, because this is really, as they say, mind-blowing what they have done. And then there is the unsupervised learning, which is simply finding some statistical correlations, or relations rather, say relations between examples of the data in a massive data set that we have. So we have an environment, all the data is given to the learning system, and the system finds some kinds of differences, say distances between examples, and groups them. This is mainly used for clustering. So there are no true data given here as true labels given here as in the supervised learning. It only we shall only use the data afterwards as, for example, clusters. And then it might be used in, so there's also kinds of learning which I have not put previously. There's the so-called semi-supervised learning, when we use in a environment which is basically it is supervised, so that the environment gives the model both the input data and the true label. And in a supervised, semi-supervised learning, we also use some of the examples which do not have a true label. And then it is usually done if an example is classified with a high level of, it is almost, the system is almost sure that the label is such as it is given. Then it is also used, well, the system assumes that the classification is correct, and then it moves the parameters in a way that it will be classified as such. And then there's another type which is too complicated now. This is a self-supervised, which is generally constructing some differences in the data in an artificial way, so that the examples from similar groups are classified similarly. This is, for example, the contrast. If you ever come across, this is the type of a contrastive learning. It is, I have used it with some of my friends, if some kind of EEG clustering. And then there are several types of problems. The linear regression, the kernel graphical model. Well, not the problems, models rather. Expectation, let's skip it. We should not have. There are even more, as I had. This is not exhaustive list. So coming from a simple model, we shall go to the deep learning and try to find why the models are are usable and why the deep learning actually works. So let's use the simplest possible neural network. This will be, I call it always a very shallow model. So we have only the inputs, weights, then there is some kind of it is a weighted sum computed with a bias, which moves it somehow, and then a classification is done out of a classification or a regression model. So if we want to approximate this function and the dots are the data, we can do it just like with using such a model and using a loss function. Something which is central to most of the models is a loss function. We always define a loss function, which is a difference between the error actually is the difference between a true label and the label computed for an example. That we shall call the label, and the error, I mean. And the loss function is a function which computes it for all examples or a group of examples. This function needs to be bounded on below so that we can always minimize it. Well, it does not need to be. It will usually be 0 when all the examples are correctly classified, but it does not need to be 0. It might be +1. The problem is only that we want it to be minimized in some way so that the gradient algorithm can be used. As you well know, this all comes from the notion of the neuron, which you know much better than I do. And then it was first proposed, artificial neuron was first proposed in 1940s, I think, by McCulloch. It was called the threshold logical unit, and it was built in such a way that all the weights here were either 1 or 0, and if we wanted some input to be more important, then there were more connections from that input. Simply, there were not one but several connections, each computed as a 1 with weight 1. That was the idea of the. And then it came in shortly that in a paper by Minsky and paper who have shown that some simple problems cannot be solved with such a model. For example, an XOR problems, which is, as you probably know. Oh, no, that is not a. Mamy tu kredę? Thank you. This is a simple classification where we have 4 examples or 4 groups of examples. These are the crosses and the circles, and we want to classify it from circles from the crosses. It is impossible to, because this model, which was here, simply is a model which corresponds to a line being drawn between most of the 1 and the second class. There is no way to put to discern the crosses, for example, with a single line. So the perceptron, as it was called, does not solve this problem. So the solution was to add some hidden neurons, and this hidden neuron used some sort of an activation function. One of the mostly used was a sigmoid activation function, which is written just as it is. It is a type of an S-type function. And there is even a theorem that says that a neural network with a single hidden neuron and an output can compute any function with any error you want, the minimal as it is. But it is an existential theorem which only says that there is such a network, but it doesn't say how to build it. So actually this is a fine theorem, but nothing more. It doesn't help us in any way. And then there was sometimes it leads to the problems of explosion or vanishing gradient in the learning of gradient, in the gradient learning. So now there is the mostly used is the so-called ReLU function, which is a function which is simply linear if greater than 0, and 0 otherwise. It is, well, it works. I wouldn't go to the details here. And then adding the new neurons, new layers, we come to the deeper network. And then the problem is, when can we say that the deep network is a really deep learning, goes to a deep learning problem? First, what we have to remember is the backpropagation algorithm. The backpropagation algorithm is actually an implementation of the gradient learning. It is a kind of a method which computes the error for the hidden neuron. If we have a, this is a, how did I write it? Yeah. It's from, here we have the inputs, then there is the input layer, then there is a first hidden layer, second hidden layer, and the output. If we had only the output with no hidden layers, it is possible to compute the gradient. The gradient means how the weight, how the output is dependent on the weight. So we can compute the error here and then find how to modify the weight so that the error will be lower the next time. But then, in case of a network with hidden layers, we can compute the error for the output neurons, but there is no way to compute the neurons. We cannot say, rather, what is the error for the hidden neurons. And the backpropagation algorithm, which came to life in some 80s, I think, 1980s, developed by Weber, came to that the backpropagation computes the hidden layer as a weighted sum of errors from all the so the error for this hidden neuron is rather like that. The neuron for this hidden neuron is a weighted sum of errors from all the neurons in the next layer times the weights that they are connected. So we can compute. So the computation goes like that. First, we compute. This is the so-called forward pass. We have the input and the output. Then we can compute the error because we have the true label. And then we go backwards. There is the output layer. We have the error. Then we may compute the modification for this one, and thus the error for this layer, for the neuron in the layer just below the above here, above the output neurons. And then we from this error we can compute errors in the preceding layer, and so on and so on. So it goes quickly because the computation is very simple. So this is why the gradient learning is, say, efficient. But we have several problems with it. Several problems with it. The backpropagation computes the gradient, but the loss function is not convex. So we have several minima. If it was convex, we shall find the optimum minimum, well, in just few runs or in one step even. But then it may have local minima, which may not correspond to the best possible solution. So first we need some algorithm which will be able to jump over the shallow minima and find the minimum which is, well, which gives the smallest possible error. And then we want to, this is one thing, and another thing is that we shall, the function, the neural network which shall have all the weights unconstrained, which will have, which may be assigned different weights, whatever weights, will compute anything, but somehow they may go, during the learning, they may go completely astray, and it will be hard to go back to the right solution. For example, if we are given a number of examples which have a minimum, well, somewhere there, but the right solution is in the completely different part of the solution space, which is usually highly dimensional. So we have to constrain it, and usually the constraints is by adding some kind of a penalty that will be the reduction of the functions that we may be computing. This is for example, the regularization by adding some sort of this is a penalty which is based on the norm of all the weights. So we want all the weights to be as small as possible below, near the the correct solution. And then I just added yesterday another picture because there was a question from the auditorium here whether we can use several loss functions in one network. Actually, yes. For example, this is a well-known inception network. That was the name of the given by. It was named either Inception or GoogleNet, which is a very deep network with some different layers, convolution, pooling. I shall give you examples of that operators. And then it has an error computed at the end. And and also some errors computed in between. And these errors keep this function space, that is the solution space, it adds some additional, adds some constraints on the solution. That was one thing, and another thing is that there are several algorithms which may be used. For example, the simple gradient descent. This is SGD. It comes not from simple gradient descent, but from stochastic gradient descent. This simply means that we are training in batches, and the batches are small batches that are groups of groups of examples, and then we go through the whole space, and this is the red line, and as you can see, it learns very slowly. Then another solution might be the so-called momentum, which adds to the current modification of the weights. It's at some part of the modification from the last step. It learns faster probably from the SGD method, but slowly, and the meanders, as you can see. This is the view of the error function. It might look like that. This is the, and then there are some other, the Nesterov function, ADA, these are not, there's an Adam algorithm which is used very frequently. The problem is how deep is deep? Well, each layer computes, how does it actually work? Each layer actually computes its own features. The idea is that from the input space, we map it into a space of features, and then from this space of features, we map it onto another space of features. So what would be the solution for this problem? The solution for this problem would be to map it first to some hidden space where all the, say with only 2 neurons in the hidden space, so that all the crosses would be mapped into here, and the circles would be mapped into here. And then the solution, whether it is a cross or a circle, would be simple. So this is simply a mapping of spaces, and then it comes into the idea of so-called compositionality, so that we compose features from features from features, functions from functions into functions, from a simple ones into the more complex and more complex. So this is a kind of a transformation of inputs, data distribution into some kind of a distribution of the features, and until we have the output. And so that if we have, this is a type of a network which has to recognize faces, so that at the input we have pictures of images of people, say, and then it computes first some very local features, and these are usually some gradients, some lines, some vertical lines, horizontal lines, gradients from the diagonal, whatever. And the features are learned. These features are learned, which are needed for the actual solution. And then the compositionality would say that from these simple features we compose something which is a little bit more complicated. Say it comes to an eye or a nose or something, and then from that we compose a face. Well, this is what I said is a very simplified solution, but we shall come to some more complicated in a moment. And then there is a problem. Why 5 minutes?
He's got 1 hour 15.
So it's for what time is it now? So it is deep linear network. I will skip it. I have to skip it. I wanted to say that the date which is considered the start of real deep network is deep learning is the time that Alex Krzyzewski and the group, they built a network which was called AlexNet, which was for the solution of the ImageNet. This is a large database of images, 280 by 280, something like that, with several different objects. And then it was built as a, I'll give you some solution. It is, I just checked, it is cited over 100,000 times already. So you use deep learning and give solutions because you will be cited several times. Yeah? 100,000, that's a number, really. But I have to skip something. One of the types of networks.
Yeah, actually, the deep learning stuff maybe not so popular at this time.
Which type?
When this
Convolution?
deep learning, you know, those networks, etc. By why this previous slide, you know, you showed us a study. Why get the other one, AlexNet? And why it is important? Because like we already knew that maybe
it is important because it used the network which was type of a network which was provided in some Nakayama, Nakashima, Yokoshima. I forgot the name of one of the Japanese for recognizing letters, and it is a type of a very deep network. Well, not so deep as for today, but a deep one, which uses convolutions in each layer and then a pooling operation. I will just provide it here because there's a convolution is an operation on a very small scale, so that it computes features for some small regions, and they are multiplied for all the picture. The same features are being searched for on the whole picture, so it is translation invariant, well, almost. And then there is a pooling operation which simply moves, well, gives as a solution to that for a small region the best solution that was found, the best image. And then this network was used just so that we shall find these classes. And there you can see that these are the low level, high level. For example, low level features for faces were found like that, and these are the higher. For elephants, we can find there's a trunk and whatever. It's hard to see, but then this is the first use of a deep network with convolutions. That is why it was so important. Why is it working actually? It is working because it is deep. It has nonlinear activations. That is one thing. And then another thing is that it uses some inductive biases, so that the network uses the convolutions which represent some small patterns of features. It is a group equivalence over space, simply. There are graph neural networks which provide for some equivariance over relations, because you can describe a problem as a set of relations. And there is a soft attention, and this is why generally so if you come across the inductive bias, this is one of the ideas of solutions which are not now found to be the most important for the neural networks to be working. One thing, this is frequent, there is no one good solution for any problem. There is no one network for any problem. You have to search. This is one thing that it unfortunately takes a long time for devise a good solution with a network, so that it takes a long time to search for it, usually. For a good architecture, good function, and a good set of weights, parameters. I just wanted to show some examples. One example is a real-time recognition of multiple elements, so that we have traffic images, or, for example, traffic images. It will be shown here better. And the task is to find, and this is a moving picture. This is a film, movie, right? And we have to find all the cars and all the people, and classify them on the as they are moving. Just find them, and we'll classify even their faces and so on. This is a very fine example of a network. But I wanted only to say that it is great, provided that it is not used for mass surveillance. You can watch the YouTube and find how the mass surveillance is done in China, and this is just done using such solutions, unfortunately. And this is, I know why in the biggest conferences, half of the participants are coming from China, because this is the best place to live. The important model is an autodecoder model, a generative model. We can build an autoencoder, which is simply, we have an input, an output which is identical, and the idea is to reconstruct the image from the input, but going through a bottleneck layer. That is a layer which has much smaller number of neurons, so that the image would be some way compressed. Only the features which are important for the reconstructions would be represented here. This might be used, for example, for compression, for speech compression. It is being used. But then, do we have any control on the bottleneck layer, the one in the. There is an idea of generative models, so that the constructions is almost the same, only in the bottleneck layer is built such that we want it to be the distribution of images from coded from the input would have a distribution similar to some other distribution. For example, the Gaussian distribution. And imagine if we code with that any sound or images of people, for example. If we code it into the layer here, so that the reconstruction is correct, then we can draw a number from the Gaussian distribution using a completely well, we can simply sample it, put it into here, find a place in this space, and reconstruct the image, which would be come from that random number. So without using the encoder. This is the how the mapping of 9. These are the pictures of images. How the images would be images of digits would be mapped onto a 2-dimensional space with a generative model. So if we sample from that square, you will always get an image, not a random noise. And the idea is that we can, how to use it. Because sampling simply is fine, but what to use it for? Well, generate new examples, but we can use it in a different way. Sample 2 examples from the space, and then do a interpolation of examples between them. And then find some examples which are similar to both the first one and the second. So that would be for example, the faces, but that is not a great use. But this might be used, for example, in chemistry, in drug design. First, we build an encoder. There is the latent space. The latent space can be optimized, for example, for the solubility of the molecule. And then we can, sampling from this space, and take a molecule for aspirin and take a molecule for ibuprofen, for example, 2 painkillers, then find something, interpolate, then find some points in the hidden space which would correspond to molecules which are between aspirin and the ibuprofen. And then we can stop doing other research, because that will make us very rich, provided that this is a new molecule. So this is an example, even ibuprofen. If we take the ibuprofen, sample it, take the place curate, and then sample molecules which are in the neighborhood of the ibuprofen. We get different molecules which are very similar to the ibuprofen. And if they are similar, then they might behave in a similar way and have a similar impact on our if brains, if we have a headache or something, which is unfortunately popular. And that would make a... But the problem is that we have to learn it, train it on a large database. But for example, in chemistry, there are a number of databases of known molecules. For example, the zinc, the ChemBL, several of them. Yeah, here is the route from one acebutolol propafin. This is a picture from the Gomez-Bombarelli group. This is one of the papers that started it all, the use in chemistry, a well-known paper, very well-known paper. We can optimize it in the interpolation. This is from a paper, I said Podolak et al., but this is also work with Professor Tabor here, and then that we had an interpolation here, which is, the interpolation was done in such a way that to find molecules which are soluble, more soluble in water. This is one of the parameters that are very important in drug design. Then we can build this encoder-decoder and add some additional properties. Encoding of the additional properties here, and then we would get something similar to this, with some properties, additional properties fulfilled. These are several models of this, how they work. Five minutes or 10 minutes? 10. 15 minutes. Another model of generative model that you may come across is so-called generative adversarial network, which also is built for the sake of generating things, but it works in a completely different way. This is what is fine. The previous model was trained to reconstruct the data that were given on the input, to reconstruct them as well as possible. That was one of the elements of the loss function. And here we have a completely different type of learning. There is a model, the so-called generator. We input some random noise. It generates something. At the beginning, it would be some sort of a noise. But then we learn also discriminate. And what we want to learn? We want to learn some representation, for example, for faces. And then we have the discriminator, and the task of the discriminator is to say, because it receives as input either the generated face or a real face from a database, with 50-50% chance. And then the discriminator is the task of the discriminator is to say whether it is a true image coming from the real database or whether it is a generated image, so-called fake. And then this is a kind of a game between us and the discriminator. The discriminator wants to be the best, to be as good as possible to discriminate whether between the true images and the fake images. And we want to make the generator as good as possible so that the discriminator would not be able to discriminate between those two. So in the end, the discriminator is as good as possible, but it will never be perfect. But this is what we want. We don't want, we want it just to be, we want the generator as good as possible so that the discriminator would not be able to discriminate. What is important here, there is no comparison between what we get and what was the input. So we do not compare the images, the input and output image. We only compare how the discriminator works, and rather how the generator is good at misleading the discriminator. So the images do not come hazy, which is one of the problems with the autoencoder method, which was in the previous slides. The encoder decoder. Oops. Some very nice examples, which are we can build a system so that it learns both an image and a description. And afterwards, when we give a description, it would build an image. There are several models like that, GPT, GPT-2, 3, Glide, DALL-E 2 was. It was, I think, developed just this year. It has about 12 billion parameters. This is a huge number. Only the GPT-2 is open. You can find the code, a trained machine downloaded. But the DALL-E is perfect, which I will show you now the examples. And these are the examples of images which were constructed from the description. The description is vibrant portrait of Salvador Dali with a robotic half face. Works? Works. A Shiba Inu wearing a beret and a black turtleneck. Panda mad scientist mixing sparkling chemicals art station. A teddy bear on a skateboard in Times Square. Great, this is how Times Square really looks like. So this is DALL-E 2, but then, and OpenAI have just designed a similar system which learns from the GitHub data. So whenever you upload your programs to the GitHub, you know what the Microsoft and OpenAI do with it. They trained a system to write programs automatically. It is not open, unfortunately. But then we can think of disturbing the weights of such a system. A friend of ours, Romek Janik, which has done it on the model, on the open model GPT-2, disturbing it with systematic disturbing. These are the disturbances of all the weights in a given way. He, for example, added some sinusoid function noise to the weights. Similar. And then giving a set of, these are the images when you tell the system to build an image for a telephone, for a coffee cup, for a pole, a coffee cup again, but this was done with a large disturbance. The idea of Romek was to build a system which would be under some influence of drugs. And I think he succeeded somehow in it. I don't know, really, whether he succeeded, whether it looks like that. And again, 5 minutes. Last example, which is really great. The example of reinforcement learning done at the DeepMind group. Atari games and games are a perfect method to test reinforcement learning. And they have done several of that. First, it was a training of for the Atari games. So there is the game and a set of possible moves to the right, to the left, and so on. Then it has several weights. I mean, this is the, I completely mixed it up. It's on the other way round. This is the image. There are a number of layers, and then there is the stick where you can move it, move the whatever it is, a robot, to right, to left, and so on. And then this is a supervised learning, and we can see that most of the games have the robot is better at playing with these games than a best human. But something which is of the highest, the best one, I think, is the AlphaGo. The Go is a very complicated game because there is the spanning tree of that game is very large. Well, the branching factor actually. At the first move, you have some 380 places where you can place your stone, and then the other player has 380, one less and one less and one less. So the branching factor of this is where to place the stone is very large. So there were some solutions, and what is nice here is that it is an extendable solution. First, it was trained with expert knowledge, and this was trained in somehow supervised way. The expert ranked what the robot has, the algorithms has done. And it even won with one of the better players. But then they started the work with the so-called AlphaZero, which learns from scratch. And then it is a combination of a so-called MCTS, Monte Carlo tree search algorithm, and deep learning. So this is a tree with all the possible moves, starting from the beginning with the empty. And then there is a move which is placing a stone in some given place, and so on. So we have first the MCTS works in such a way. First it selects some move, then it expands the tree randomly just to the way to the end, so it places randomly the stones and finds the solution whether one of the player which has selected the move won then there comes a reward 1 or 0, and it is moved up so that the selected move can be ranked, whether it is correct or incorrect. Well, it goes to the, it results in a winning the game or losing it. But they have built neural networks, deep neural networks, this is why it is called deep, so that they would evaluate the result at all the nodes. And then this is one thing, and the model started to play against itself. They had a pool of these solutions, and algorithms, different solutions of the same algorithm played against itself. And then the best was found, and then they played again against itself, and so on. And this algorithm, Alpha 0, it has won with the best player over the world, Lee Sedol, the Korean Lee Sedol. He looked angry. I've seen the movie about that. He looked really angry. And then the solution, just 2 minutes. The solution was used to learn to play chess, and it was very quick. Chess is much simpler than Go. Then there is an alpha star which learns some dynamic games like StarCraft, better than any human. These are the people who have made it possible. This is David Silver, who led the group. And this is Demis Hassabis. He is a neuroscientist from Gatsby Institute. He is the founder of DeepMind. And then they just recently, well, a few years ago rather, they have devised a method. This is called an AlphaFold, which is an algorithm for predicting the 3D structure of 3D folding of proteins, and it has now, as I've read, about 90% accuracy. So it's really great. The one thing that I wanted to show you only, but where is it? Oh, I've lost it somewhere. Oh, here it is. They have found that the Go algorithm, during the learning, it started to learn better and better, and it started to learn just like people learn. First, it was some sort of moves, I can't remember now. I think the capturing of stone was one of the goals of the algorithm. Then the collecting the areas, then it was balancing. So it was better and better, just like it was playing better and better, just as people do, and found some solutions which were completely new to experts in Go game. And this might be shown in another, I will show you. How do you do it? This is an Atari game, and remember, the algorithm doesn't know the rules. It doesn't know what is the goal actually. It only learns from the reward which are given at the end. And the idea here is that we have a ball and it has to break through the wall. And it found, this is also from DeepMind, Demis Hassabis was showing it at some conference. This is just after, and he has a palette here, so that just after 100 episodes of training, after 200. Well, a little better because if more frequently, after 400, well, the ball almost never drops down, but the solution is just so-so. But in the next step, the algorithm will find a strategy. And the strategy is fantastic. Just see. What is the strategy? It's the simplest possible, the best possible strategy. Thank you. I'll be open here for questions, but I don't. Yeah.
So
No.
do you have any questions?
I'm here so that you may. Mm-hmm.
If you, and you will be next.
Okay, so yes, I had a small question in the chem informatics algorithms you showed. So generally when you have these optimization algorithms and stuff, the data you given is, at least the inputs are somehow continuous. So you can change the weights in some, differentiable landscape and find the minima.
Yeah.
But I was thinking these molecules are kind of discrete. You can't really continuously go. So how do you?
Yeah, there are two main solutions. One solution is to simply discretize the space so that we, from the random sample here, we decode it and then find the best possible, the nearest possible molecule in the space of possible chemical molecules. It is done very easily with some outside tools like the kits and other tools. And the other solution is to start with a network which always produces only correct solutions. One is the so-called JT-VAE. This is junction tree variational autoencoder. Junction tree means that simply these molecules are composed as a tree that gives the relations between all the atoms inside, so that it is represented actually as a kind of a graph. So, and it returns a graph, and the graph is always, this graph is always correct. These are the main two solutions.
Okay.
Some variations about that.
My
Thank
question is about recurrent networks. Since the brain is highly recurrent, you briefly mentioned that they can be used, but you didn't really talk about what specific advantages in deep learning one can gain from recurrent networks. If you could comment on that. Recurrent, like.
The recurrent networks. I wanted to say something about that. The recurrent networks are mainly used for problems which are time dependent. So if you want to do some kind of a sequence processing, then the recurrent networks come at hand. That is, for example, what was Friedemann was talking about was the solution when we have the inputs given as spikes. And these are trains of spikes. And the trains of spikes can be computed best, I think, as a recurrent network, because the spikes come into it, and then they are computed one by one. I mean, some small small delta t, and then computed one by one with a hidden space, with the recurrent network activations working as a hidden space. So the hidden space is actually represents the current space of the transformation of the input. And so that the longer we get the input from some networks, from some input neurons, the network becomes more sure about some answer. So this is the main application of recurrent networks. But then the recurrent networks are somehow problematic. They might be troublesome. But then now comes the so-called transformer. You might have heard. The transformer is an algorithm, an architecture with an attention module, just like attention in psychology. And then it computes for a long series, but not as a recurrent network, which is great, because the recurrent network usually takes a longer time. And then the recurrent networks are really frequently used in the natural language processing, so that sentences are given as number of tokens, and then you have to, for example, to answer whether say sentences from some reviews of movies, and then the question that the machine has to answer whether it is a positive or negative. This is a common task, whether it was a positive review or a negative review. But the review can be long, and it is not set beforehand whether it has 100 tokens, 200 tokens, and it can be as long as possible. So you can process each token, each word, one by one, and develop the solution for the problem, positive, negative, for example, or translation. This is the main areas that recurrent networks are used.
So thank you once again, and let's continue discussions over the coffee, and let's come back 10 to 11. Is it okay, Daniel? 5 minutes later. Okay, thank you.